Okay, so okay, so we will be dealing with the heavy hitter nodes and heavy hitter triangles, and we will be dealing with them separately. Okay, so now as I mentioned that we have two stages, the pre-processing stage where we want to organize this data in such a way that we can quickly figure out things, and then triangle counting stage. Okay. So for pre-processing stage, okay, what we do first, compute the degree of each node, okay, because that's the first task that you have to do. And why we want to do this? Because we want to know, or rather we want to separate heavy hitter nodes from the non-heavy hitter nodes, okay. So because there are n edges in the graph, okay, we can just achieve this particular thing in order of m time complexity. Okay, that's the first thing. So that will help us separate out heavy hitters from the non-heavy hitter nodes. Now the second, we have to create an index on edges, and the index will consist of the pair of nodes, okay, as the key. So why we need this? We need this to quickly find out that if an edge between two nodes exists or not. Okay, so you have to maintain a kind of some kind of data structure. In this case, I'm using hash tables, so that hash tables lookup is very fast with two nodes as the key. Okay, and so that whenever two nodes come in, we can quickly figure out that okay whether there is an edge between or not. If we can find that in the hash table, then there is an edge. If we don't find it, then there is no edge. That's it. And again, this is also time complexity order of m, given that number of nodes and number of edges at m. And third component in pre-processing stage is basically adjacency list for each node V. Because this is the list which is going to tell me for a particular node which are the nodes adjacent to this particular node. Okay. And as you know, you have to maintain the adjacency list for it. Okay. And so this is essentially time complexity in order of degree of a particular node V. Okay. So these three things will be required in the pre-processing stage. Now, the next step is to compute the triangles, the actual triangle we will be doing. Okay. So let's, as I mentioned that we are dealing with these two kinds of nodes, the heavy hitter nodes and the non-heavy hitter nodes differently. So first we deal with the heavy hitter triangles, okay, the heavy hitter nodes. So in this step, what we do, now we find out the triangles from the most dense regions, okay. So we take the heavy hitter nodes. So all the nodes that we are going to consider in this case is all heavy hitter nodes, that I would say H. Okay. Now you simply take all three possible nodes in H. Okay. And simply because you have all like three nodes, like say A, B, and C. Okay, all possible three nodes from H, set H. And simply you want to check whether there is an edge between these three nodes. And how you can do it? You already maintained a hash table with the edge information. Okay, the pairs of nodes, and if the pairs of there is an edge, then pairs of nodes will be there in the hash table. So you can very quickly figure out in constant time. You can figure out given a particular edge or given two nodes, you can quickly figure out in constant time that whether there is an edge between these two nodes or not. Okay, so that's a pretty fast approach of doing that. Now, because like there are m number of edges total in the graph, and we already seen the total number of the maximum the degree of the heavy hitter node is 2 root over m, and so we are considering three things at a time, a, b, and c in this case. So the complexity is going to be order of m to the power 3 by 2, where m is number of edges. It's also pretty simple. You can quickly verify it. All right, so that's the most dense part that we are dealing with, where we can find most of the triangles. Okay, so the exhaustive mechanism we are applying here, but because these numbers are going to be very small, you have very small number of nodes in a graph. so you can afford that time. Now the second part. The second part is basically the counting triangles on the non-heavy hitter nodes. Okay. So in this case, what we do, we use a separate strategy than what we have done before. So you take an edge B and B1 and B2, because triangles you need to have 3 nodes, and so B1, B2 you take, and then you can take another node. So B1, B2 such that at least one of them is non-heavy hitter. Okay. So that, and then you can order these nodes B1 and B2 based on degree. For example, the B2 has a higher degree than B1. Okay. And then what you do, we can consult the adjacency list of node B1. Okay, because both B1 and B2 we have already kept the adjacency list, okay, in our data structure. So you can consider the adjacency list for node B1, the node having the smaller degree. And then because you already know that B1 and B2 is there is an edge, so all you need to check that whether all these U's, U1, U2 or UK will have edge with node B2. And that's the only thing that you need to do in this case. Okay, so essentially this is checking that U1 and B2, whether they have an edge, then whether there is an edge between U2 and B2, and U3 and B2, and up to UK and B2. So that's what you really want to check. So there are essentially there are k nodes in the adjacency list of say node B1. Then you need to have the key operations for B2. And again, because you have maintained the whole thing using a hash table, this is pretty efficient. Okay. So again, you can find out the time complexity of this one. So as you know, this for heavy hitter nodes, the maximum non-heavy hitter nodes, the maximum number of adjacent nodes could be root over m. So the time complexity for step 2 would be order of root over m, and there are total m edges. So total time complexity would be m into root over m. Okay, so that reduces the time complexity greatly for this triangle counting algorithm. But the one thing that I would like to emphasize is that the triangles that you are going to get using this approach is not the exact number of triangles. In a situation where you need exact number of triangles, then you can go for either the node iterator algorithm or the edge iterator algorithm, but not this one. But this is applicable, or this is good. This is a good algorithm in a situation where you have to deal with very large graph with too many nodes, too many edges, and so on. Okay. All right. Now we are going to look into another very fast algorithm for community discovery, and this algorithm is actually a randomized algorithm. Okay. So far, the algorithm that we have seen not randomized; they are deterministic algorithms. Okay. But now that we are going to see randomized algorithm, this is a pretty fast algorithm to partition a particular graph. Okay. Now the approach, the fundamental concept that we will be using in this case is called the minimum cut in the graph. Okay, those who have taken some kind of graph algorithms, or maybe comparison students who are familiar with minimum cut, but quickly just to introduce the definition of it. So minimum cut of a graph is basically the partitioning of nodes into groups. Again, is partitioning between two groups, S1 and S2, so that the number of edges between these two groups are actually minimized. Okay, so the crossing edges between these two groups, you want to minimize this. That's called minimum cut. Okay, so here is an example. You have the 8 node graph. Okay, and then this is one minimum cut partitioning of this graph, because as you can see that you can split this graph into these two components. There are only 2 edges crossing, edge BC and FG. Okay. So the minimum cut value in this case is actually 2. Okay. All right. Now again, this is so it's kind of based on partitioning approach. So what we do is just like the Gilbert-Newman algorithm. So we start with the bigger graph, and then we gradually split this graph into smaller parts. Okay. So in a sense, this is a divisive algorithm, hierarchical divisive algorithm. So what do? We use a minimum cut algorithm to break a graph into 2 sets. The basic idea is basically use this minimum cut, and there are many minimum cut algorithms. Okay, and I'm going to talk about a very fast algorithm for finding minimum cut in this case. Okay, it's a randomized algorithm. So what you do, you use a minimum cut algorithm to break a graph into 2 sets. Okay, and once you have the two sets, just like Girvan-Newman algorithm, what you do, you again use this minimum cut algorithm on the smaller graphs to break these graphs even further. Okay, just like Girvan-Newman, you are breaking the graph in Girvan-Newman is based on the edge between this value, but in this case we are going to do that using the minimum cutting. Okay, so this is very simple steps of this algorithm. So this key concept in this algorithm is called edge contraction. Okay, that is the key concept that we use. It's called edge contraction. So what it is? So you just repeat until convert or just two nodes remain. So you pick an edge at random, randomly choose an edge, and that is why it is called randomized algorithm. You just pick an edge in random, and then what you do, collapse its two endpoints into a single node. That means you put together the two nodes, which are basically the endpoints of this edge that you have chosen, into a single node, and then you simply proceed. And I will show you an example in next few slides. You will understand this point. But the main idea that we are making use of, there are two things you have to remember. One is that this is based on edge contraction, this mechanism, and the second, which edge we are going to contract next is determined by a random number generator. That's called the randomized algorithm. Okay. All right. So yeah, so randomized decision, which edge to be chosen next, and edge contraction, collapsing two endpoints into a single node. Okay, that's two things that we'll be using there. All right, now here's an example of edge contraction. So say we have this original graph 1, 2, and 3, and you can see these connections between the nodes. Okay, and say we want to contract this edge 2, 3. Okay, now after contraction, what will happen? Okay, so after contraction, it will look something like this. You are putting these two endpoints of the edge into a single node 2, 3, and then you appropriately adjust now the edges also, because initially you had only single edge between any two nodes, but now you have this basically multiple edges, which is also people call this multi-graph. Okay, that means the number of edges can be more than one between any two nodes. So why this happening? Because initially you had edge between 1, 3 and 1, 2, and you want to maintain that. Okay, after reorganizing this graph after edge contraction. Okay, and that is the key principle that we will be using. Okay, so this 2, 3, this grouping thing is going to be used in this case to find out the minimum cut things, and which will ultimately help us to find out the graph partitions. Okay, now let's try to understand this algorithm, a simple algorithm, through an example. So this is the original graph, for example. There are 8 node graph that you can see. Okay, unweighted, unedited graph, and the first thing that you have to do, we have to choose one edge randomly. Okay, so because there are 14 edges total, now the probability that any edge will be chosen is 1 by 14. And in any randomized algorithm, as you know, you basically generate the probability value using a random number generator. You have standard libraries in Python, C, and everywhere. You can basically generate a random number, and then based on this, you can basically choose a particular edge. Okay, so this any edge will be chosen with probability 1 by 14. So you, for example, you run a random number generator and it gives something, and based on that you pick, say, for example, the edge B and F. Okay, that's the first step, B and F you choose. So if you choose the edge B and F, that's the edge, like the next thing would be that you have to basically contract this particular edge. Okay, so if you contract this particular edge, the picture will look like this. Now you are going to put together B and F, the node B and F in a single node. Okay, and then you have to readjust these connections. Now you can see that there is a parallel edge, the two edges between A and BF and E and BF, because originally you had all these connections in the original graph. Okay, and that is the main concept in this case. Make sure that you understood this particular point. Okay, all right. Now, next, what we do? Again, we have to choose one edge randomly, of course, with probability values that we can find from this particular graph structure, and then do it. So in this case, say there are now 13 edges, okay, and say we have to run this random number generator, whatever you have in your library. So say we pick the edge GH with that probability, and of course the probability will be 1 by 13 because there are 13 edges and there is only one edge between G and H, so it is 1 by 13. Okay, so you choose, say, for example, G and H, and then you contract these two edges again. So if you contract this, your graph is going to be like this. Okay, so you are going to put together G and H together, and then you readjust your edges and all in this particular graph, and going to see like something like this. All right. Now next. Now say now we have how many edges? Now we have there are 12 edges in it. Okay, and say again you choose randomly choose a particular edge. So in this case, for example, you choose the edge D, G, and H. Okay, and the probability value in this case of picking that is 2 by 12 because between D and GH there are two edges. Okay, because they can see these two edges, there are two edges, two parallel edges, and total number of edges basically 12. So the probability value will be 2 by 12. So you can basically choose that particular edge with probability 2 by 12. Okay.
Sir,
So
I have one question.
Sure, go ahead.
Sir, why are we treating them as two, sir? The age between A, D and GH.
Okay, so it is essentially this number of connections between these two groups.
Sir, we have collapsed it earlier, like. So they should be treated as one now.
The reason is that you have to keep in mind the ultimate objective. Ultimate objective is what? That basically we are going to basically figure out the minimum cut. That's our ultimate objective. That means we want to group the elements or the nodes such that the within group connections are high, right?
Okay.
That's the ultimate objective, right?
Okay. Yeah.
Now, if that is so, then basically whenever we are basically trying to put this one together, these connections are going to give you that information, the number of connections. So if you simply discard the number of connections between two nodes, in this case the hypernodes rather, because one node will have multiple nodes, then you are not going to get that information from this graph. Does this make sense or still have doubt? Okay. All right. So then what we do, we can again collapse these two together, D and GH, and we are going to see something like this. Okay. Now, because you asked this question, I would like to now elaborate that point a little bit. Now, why we are doing that? Now, why the probabilistic algorithm in this randomized algorithm is a kind of reasonable thing to do. Now, remember this, whenever we are choosing a particular edge randomly, we are choosing this based on a probability values, and the probability value will depend on the number of connections, parallel edges between two nodes that we have. So of course, whenever you are basically taking a decision based on randomized the probabilistically, then at any point of time, the probability will be highest for a particular edge where you have too many connections. Okay, because that is the way we are computing the probability. So as a result, it is highly likely that two nodes will be collapsed together, which will have very high number of connections. In other words, high number of connections means that they are a good community. Okay. So basically, they can be treated as a part of the same community because there are a high number of connections. Okay, and that is the main intuition in this particular algorithm. If there is only one connection between two nodes, you're probably not going to put them into single like node, treating them as a single member of single community. But there are too many connections between like two hypernodes and all. You can say that there are too many common neighbors and so on, and therefore you can put them together. Okay. So in this case again, like we again compute these numbers. So say in this case we choose AE. Okay, because this is a probabilistic algorithm. Okay, so you cannot guarantee that always the highest probability or the edge having the highest number of connections will be chosen. You cannot guarantee that, but this is highest likelihood of being chosen next. But anyway, say you choose now AE, and of course the probability will be 1 by 10. Okay, and you collapse these things together. Same approach you do this and so on. In the next step, you have 9 edges total. And so the probability that the edge will be chosen, AE and BF, is 4 by 9. So you again collapse these two edges together. You're going to get something like this. And finally, if you do this, then again, like you can basically collapse this C and DGH with probability 3 by 5. You collapse this together and you are going to get something like this. Okay? And so this is the stopping condition. The moment you are getting two hypernodes, okay, I will call hypernodes because now the nodes will have multiple nodes inside it. So the hypernodes, okay, the moment you have these two nodes, you basically stop because you have nothing to do now. Okay, basically you are done. Okay, your objective was to partition the graph into two so that you have the minimum cut thing, and you have achieved that, and so you can stop now. So in this case, the ABEF and CDGH. So ABEF is part of one community and CDGH is part of the other community. Okay. And so that is how you can basically use the randomized algorithm to figure out kind of split the graph into two coherent communities. Okay. Now, before I proceed to the next part, so here basically just 2 nodes, you stop here, and so the cut value in this case is 2 because the number of now these edges is 2 in this case, so that's the cut value. It may not be the minimum cut value. I would prefer to call it a cut value. Okay, so that's the cut value ultimately that you get. Okay, but before I move on, an important note for this algorithm. Now remember that this is a randomized algorithm. Okay, now I do not know how many of you have experience dealing with randomized algorithms. So randomized algorithm are typically like if you run multiple times an algorithm, randomized algorithm, you are going to get multiple, you may get different outputs. Okay, it's not like deterministic algorithms every time for a single input, same input, you're going to get the same output. Okay, so because your decisions are typically determined by the random number that you are generating at every point of time. Okay, so then what we do? Now therefore, for good results, what you do, and because it's a randomized algorithm, it doesn't guarantee that you are going to get the minimum cut value. But this is a fast algorithm, we can quickly do it. That's why it is like very fast algorithm. But it doesn't guarantee that you're going to get the minimum cut value. Okay, so what do you do then? So we should do this, and simple like trick that you can do, we can run this algorithm multiple times. Okay, so if you run multiple times, you are going to get multiple cuts. It's going to produce multiple cuts. Okay, for every run you're going to get one cut, and then of course you take the cut with the minimum value. Every cut for everything, for every run, you are going to get the cut value. Okay, so if you run it n times, you're going to have n values, and you choose the one having the minimum value. Okay, that is still may not be the minimum, actually the global minimum or the actual mean cut value. Okay, but again, I mentioned when you are dealing with a large graph, little bit of sacrifice on the accuracy is perfectly all right if you can achieve these things very quickly. Okay, and that is what we do in like all the time when you're dealing with a large volume of data. Okay, and so this advice, this suggestion is not only limited to this Kargar's min cut algorithm only. So this is true for most of these randomized algorithms that we deal with. Okay, whenever you have to do something using random number generators, you run multiple times and then you choose the one which you think is the best based on some criteria. Okay. All right. Now, so that's more or less from the community thing. So now we are getting into the representation learning on graph, and that is like more like recent things compared to the other ones. Okay. So you have probably have heard of that representation learning on natural language, on these, on image, and all kinds of stuff that you have seen. Okay. So essentially, you want to represent a particular image or particular word or particular piece of text into a vector. Okay. So if you have text data, you can convert the text data into a vector. So be it sentence, word, paragraph, whole document, whatever. If you have an image, you want to convert the image into a vector, and people have been doing these things for last few years because of deep learning, advent of deep learning. Now we're going to see similar kind of thing on graphs. Okay, so representation learning on graphs. And why it is important? Because once you represent, essentially converting these nodes and edges in terms of the vectors, then we can do most of the things that we have seen so far very conveniently. You can figure out the similarity between two nodes, similarity between two edges, and so on and so forth. Okay, so there is this like the main objective that you have the input graph on the left side. Okay, you can see these things. Okay, and as an output from this algorithm, the representation learning, what we want to get, we want to convert this graph, okay, into a kind of set of vectors. Okay, so for every node, we will represent every node in a fixed dimensional vector space. Okay, so in such a way that that the nodes in the graph, the similar nodes in the graph have similar vectors. Okay, if two nodes are very similar in a graph, original graph, when you convert these nodes into vectors, the vector will also be very similar. That means the angle between these two vectors will be very small. Okay. So here is the setup that we assume. Assume that we have a graph G, and so B is the set of vertices, and A is the adjacency matrix that we have. Okay, in this case, telling these connections between the graphs and so on. And our goal, the primary goal would be to encode the nodes so that the similarity in the embedding space, like the space that you are giving, so you are converting these nodes into vectors. So you have to encode or embed these nodes in such a way that the similarity between nodes on the embedded space will be approximately equal in the original network. Okay, so for example, if you look at this particular picture, what happens in this case on the left side of the graph? So U and V, these two nodes are neighbor. Okay, they are neighbor to each other. Okay, now what I want to do, or what's the expectation from this algorithm is that whenever you are projecting this U and V and all other nodes on the vector space, then the vectors of, say, for example, ZU, U is ZU and vector for V is ZV. So this vector ZU and ZV will also be very similar in the sense that the angle between these two will be small. Okay, because U and V are the neighbors. Okay. On the other hand, if you consider other nodes, for example, U and some node from the left side, then the angle should be very high. Okay, so all we want to do, we want to come up with an encoding mechanism, automatic encoding mechanism, which will take the graph and then it will produce the fixed dimensional vectors for all of these nodes that you can find in this graph. Okay, so that is what we want to do. All right. Now, for this, we need to have a measure, similarity measure. So similarity measure that we use is dot product we use in this case. Okay. So essentially, so say for example, ZV and ZU. So this capital Z means this capital ZV means this vector, the desired vector for the node V. Okay, on the embedding space. So what we really want to do? We want to basically approximate the similarity between two nodes U and V from the original graph in terms of the dot product. Okay, so Z transpose, ZV transpose and ZU is essential dot product between two vectors. Okay, so that would be our ultimate objective. We want to approximate this similarity, original, but to maintain that kind of similarity, once we encode these nodes in a vector space. Okay, so that is what we want to do. Now, again, it stands on three simple steps. First of all, it's an encoding problem. So we have to define an encoder. So encoder will basically map the nodes to embedding space. The second is basically define a node similarity function, okay, which will compute the similarity between two nodes. And third step essentially, or the very obvious step, you have to optimize this parameter of this encoder so that you can actually approximate the similarity between two nodes U and V in terms of the dot product. Okay, so that is what basically we want to do. The three simple steps you have to do. The key thing again you have to remember the similarity U and V approximated by the dot product of these vectors. Now we do not know yet how to find ZV and ZU because that we have to basically figure out. Okay, U and V, similarity between U and V could be figured out. For example, if you have a simple graph, you can probably figure out that how many common connections they have, the distance between two nodes in the graph in terms of the number of edges and all kinds of stuff. But we still do not know anything about ZV and ZU. And our goal would be in this case to figure that out. Okay, the values of ZV and ZU for all the nodes in the graph. Okay. So again, the encoder essentially the mapping from a node to a vector. So I denote that ZV, which I already mentioned. And the similarity function specifies how relationships in the vector space map to relationship in the original network. Okay? So similarity function could be many other things, but here we are taking dot product similarity, which is very common. All right. Now broadly, there are three possible approaches that we are going to discuss in this. The first approach is adjacent neighbor based similarity, and then multi-hop based similarity and random walk based similarity. Okay, these three things like we're going to talk about. Okay. Now let's look at the adjacent neighbor based similarity. How to do that? So the main thing that we need to keep in mind that we have to define a loss function because we want to represent this original graph on an embedding space so that similar nodes are similar. Okay. And so therefore, how we basically find out these vectors ZU, ZV, and all other nodes. Okay, that's very crucial thing. And our objective would be to retain as much information possible when you are encoding these things. So for that, we need to define a loss function. Typically, that loss function you probably are familiar with in most of the machine learning cases. The same thing. So what you do, the loss function in this case is defined as this, that for every pairs of nodes in the graph, for every edge in the graph, which is essentially pairs of nodes, okay, we have the dot product similarity based on the vector that you want to get, and AUV is the adjacency matrix for that particular graph. It could be weighted, it could be unweighted. Okay, whatever, it doesn't really matter. Okay, if you're dealing with weighted graph, AUV will be weight values, otherwise it will be 0 and 1, something like that. Okay, so what do we really want to do? This is our loss function. So we have to find out ZU and ZV in such a way that when you compute this expression, then the value of L will be minimum. So how can you find those values ZU and ZV? And as you know, ZU and ZV, they are parameterized, okay, because we are basically finding out the fixed dimensional vectors. Okay, essentially ZU will have, say, if you have, say, d-dimensional vector, it will have d parameters. Similarly, ZV also have d parameters and so on. Okay, and so therefore that you have to do. So we now have the loss function, and because this is a loss function, you can straight away use the stochastic gradient descent as the general optimization method. Like stochastic gradient descent in machine learning, this is very standard optimization technique that you can use. So you can randomly initialize these ZUs and ZVs, and then you can apply the stochastic gradient descent to find out what would be the good values, final good values for ZU and ZV. Okay, so that is how you can basically make use of the only neighbor things to figure out the embeddings. The second case. Now the drawback of this approach, what is the drawback? The first drawback is that you are considering that all possible pairs of nodes. So runtime is very, very high. If there are mod v number of nodes in the graph, then the runtime is going to be mod p squares, this is quadratic. Okay. And the second is that you are only considering the direct and local connections, not more than that. Okay, just direct and local connections that you are doing. So therefore, what happens is that you are not making use of this. For example, the nodes which are little farther from me. Okay, and those nodes can also give some additional information, and which we are basically missing altogether. Okay, we are not going beyond one hop thing. So these are the two main drawbacks of this particular approach. Now, in order to avoid that, so this slight refinement of this previous approach is called multi-hop similarity based approach. Okay, so in multi-hop, what you want to do, rather than single hop neighbors, my immediate neighbors, I want to go like k hop up to k hop, 1 hop, 2 hop, 3 hop, and so on and so forth. Okay, so you can, for example, if the red node, okay, is the target, I mean my target node for which I want to create the embedding, then my 1 hop neighbors would be the green nodes because distance 1, okay, 1 from my red node. Then 2 hop neighbors, the blue nodes, which are 2 distance apart from the red node. Okay. Then the 3 hop neighbors, the purple nodes, which are 3 distance apart from the node, and so on and so forth. So all now we have to do, instead of only using the immediate neighbors in the loss function that we have seen, we want to use all these nodes. Okay, all these nodes, 1 hop, 2 hop, 3 hop, and it depends on the what would be the hop length for you. Okay, by increasing this hop length, you can basically take more nodes and so on and so forth. Of course, there will be other problems as well. You have to maintain a balance between how much you want, how further you want to go from the target node, and so on. But essentially, like increasing the space of this number of nodes in this case by taking into consideration the hop information. Okay, and which again you can use the same loss function that we have seen before to address this problem. Okay. So I see that I have 2-3 minutes left. I have to tell you a few things about your examination next week. So I will stop here. If you have any question, you can ask on this. Otherwise, I will briefly talk about the examination next Monday.
Hello, sir.
Hello, sir. Yeah, please go ahead.
Sir, why are we taking dot products as similarity measures? Rather, we can take cosine similarity to measure the angle.
Yeah, so that's a good question. You can do that, but then there are two reasons for that. So cosine, when you are taking cosine similarity, then there is a denominator factor that you are taking. So, and for optimization angle, that is relatively difficult to optimize. The expression becomes little complicated, and so good. But the issue is that there are some ways you can basically take these vectors on, say, people all call on like the unit hypersphere. Okay, there are some ways you can manipulate that, and once you make sure that, then the the denominator part in cosine similarity is not relevant, and so dot product is actually a good thing. Okay.
Okay.
Yeah, of course, this dot product is not the final thing. There are other measures that you can make use of, but this is the most popular one people use. Okay. Any other question? All right. So let me stop, and then I will briefly talk about your examination and all.